So now that you know this, okay, share. Here we go. Huh. So, welcome back. So as you can see, I'm starting with chapter 2 rather than chapter 1. I mentioned this briefly yesterday. Um, Editorial choice. Um, I think chapter 2 is much simpler in a sense than chapter 1. And so it makes more sense to me to start over here, especially since you will have seen bits and pieces of this. Okay. So this is basic set theory, um, which is the basic language of math. So all of modern mathematics is based on set theory. This is like the if you're more a programmer type, this is the assembly language of mathematics. Okay. Originally, due to a German mathematician, Georg Cantor, mid 19th century, it was later formalized by Zermelo, Frankel, von Neumann. There were like little itty bitty, tricky little problems that had to be fixed. We're not going to go into the technical set theory of the 20th century. It gets heavy and deep and it's not necessary for us. So, what we're going to be looking at is usually called naive set theory, which is fine for our purposes. I will let you know about one little problem you have to be careful with, which is not going to be a problem for us, but you'll see why it was required that a little bit later that people had to think about set theory a bit more deeply. So there are three sections in chapter 2 that we're going to look at. The first 2.1, just basic definitions of sets. 2.2, we'll look at how we can combine sets to create other sets. And then we'll talk about functions, which are, in a sense, special kinds of sets. Okay. So here we go. Basic definitions. So I'm using slides for this because it's a lot of definitions. There's not a lot of computations or anything like that. So what is a set? It's a collection of objects, and the objects in the set are called its elements or members. And this is a notation that you have probably seen before. Sorry. Yes. Um, that's not what I wanted to do. Sorry about that. Okay. Um, so the notation you see there means that little a is an element of the set A, and if you have a bar through the round E, it means that little a is not an element of the set A. Okay, and our basic definition, and this is, I mean, this looks silly the way it's written, maybe because it's like obvious, but we'll see later that in terms of proofs, this is a very important definition. So two sets are equal precisely when they have the same elements. Okay, and I'll get back to that. You'll see when we talk about the exercises and showing that two sets are the same. This is a definition that's going to come back. Okay, when we're describing sets, obviously the most efficient or most down to earth way of describing a set is just to list all its elements, right? So that's what a set is. It's a bunch of elements. So for example, if I write, yes, the slides will be available for sure after class. Absolutely. Um, so if I write these curly brackets, what's inside the curly brackets is the list of the elements of the set. So big A here is the set that consists of elements 1, 2, 3, 4, 5. Now, when we're writing this down, the ordering and the repetitions are not relevant, right? So if I repeat the same element several times, it makes no difference whatsoever. And the order in which I write the elements makes no difference either. So if you look at the next line over here, so the set consisting of the elements 1, 2, 3, 4, 5, here I've written several times the same elements, and here I've written them in a different order. It makes no difference. It's the same set because they have exactly the same elements. Okay. Another way to describe a set, which is more common because most sets are too big to list all possible elements in the set, is to describe the elements by some property, some defining property. So this is something you've seen also probably for intervals and subsets of the real numbers. But here the set B, so how do you read this? This is the set of all x such that x is a positive integer. So an element of B is any positive integer, okay? Another example here is the set C, which consists of all elements x such that x is an airline, which has a direct flight from Montreal to Frankfurt. There are two such airlines, which are Air Canada and Lufthansa. So I could write the set in two different ways here. It's such a small set that I can list all its elements, or I can give this defining property for the set, okay? Now, often we cut corners when the rule that we are describing is obvious. We might use three little dots. For example, the set B that I gave earlier, the set of positive integers, I could write the set consisting of the elements 1, 2, 3, 4, three little dots, okay? And here's another example, the set x such that x is a positive integer less than 100. We might very informally write curly bracket, 1, 2, 3, three little dots, 98, 99. It's clear from context that we're talking about positive integers between 1 and 99. Okay, so you might see this also obviously, but it's informal, right? It's just to go faster. Okay, some special sets. You've seen most of these. They come up so often that they get their own name. So the empty set, that looks like a very useless set, but it's actually a very useful one. The empty set, the most common notation is the first one that I put there, which is a sort of the Greek letter phi stylized, like it looks like a zero with a bar in right through it. So that's the empty set. You might see also the notation, which is two curly brackets with nothing in it. So that's the set which contains no elements whatsoever. The natural numbers, these are the positive integers together with zero. The standard name is n for natural numbers. The integers you've seen before, obviously. Z, if you've been wondering why it's called Z, if you speak German, you don't wonder. It's totally natural because in German, number is Zahl, which is written with a Z, Z-A-H-L. So that's why it's called Z. Q, the rationals, these are the fractions, right? R, the set of real numbers, and there's also C, the set of complex numbers, which we might see informally at the very end of this course if I want to talk about a little bit about quantum computing. That's where it happens. You need the complex numbers to talk about quantum computing. In this course, the last two we will not use very much. Even the rationals we're not going to use very much. So I was telling you yesterday about discrete mathematics. So natural numbers, integers, maybe fractions, real numbers, complex numbers, not so much, okay? And again, somebody asked the question yesterday, a good question, how much calculus do you need to know for this course? And it's basically not at all, okay? Okay. let's talk about sets of sets and universal sets. So the way we've defined sets, their elements could be anything, right? So in particular, they could be other sets. So here's a set. The set D consists of 4 elements, which are themselves sets: Z, Q, R, and the empty set. Okay, that's legit. That's allowed. That's fine. Um, it can get a little confusing. Okay, some of the exercises you'll see will be a little tricky. You have to think about things, which also makes it a bit more interesting. But anyway, um, now in it's often very convenient to have a set of reference which contains all the elements we're interested in a given situation. Okay, this we will call the universal set. It depends on the context. So it's really tempting to say, well, let's talk about the set of everything. Okay, so that'd be useful, just a set which contains all the possible elements we'd like to talk about. But if you try to do that, you're going to run into some major problems, and I will talk about that perhaps today, perhaps next time. I think today I'll tell you about it. It's kind of cool. But you're going to get into trouble if you try to do stuff like that. Okay, we'll get back to that later. Okay, Venn diagrams, also known as potato diagrams. We draw potatoes. So this is not formal math. This is just a way for us to visualize sets, which is useful. Okay, so we represent sets by drawing discs or potatoes. The universal set would be represented by a rectangle containing everything, right? And elements of sets are represented by points. And if they're inside the potato, it means it's an element of that set. And if the point is outside the potato, it means it's not an element of that set. Okay, so here's a very simple example. You may have, there are tons of jokes on the web using Venn diagrams. So here's an example where the universal set consists of the elements 1, 2, 3, 4, 5, and the set A consists of elements 1, 2, 3. Okay, so that's a simple example. Okay, inclusion. Another definition, very simple definition. Again, I presume this is something you've seen before in one form or another. So the set A, we say, is a subset of the set B if every element of A is an element of B. Okay, so the notation is right there below. And I'm throwing in this extra proper definition, of a proper subset, which is not very deep either. So we say that A is a proper subset if A is a subset of B, but it's not equal to B. So notice that a set is a subset of itself by definition, right? Every element of A is an element of A. So A is a subset of A. That's always true. And if I want to talk about subsets of a set, which are not the whole set, then I say they are proper subsets. Okay, so you have this notation there. Think of less or equal, right? It's the analogy with less or equal and strictly less. It's the same thing. Okay. Now notice this is really important. When we get to chapter 1, we'll talk about this a bit more. I want you to think about this in terms of existence of things. So look at the definition there, and it says something about every element with a certain property also has another property, right? Now, if you negate this, so we'll say that A is not a subset of B, what does it mean? It means that it's not true that every element of A is an element of B. In other words, it means there exists some element of A which is not an element of B. So we went from every to there exists. So this duality, when you're negating, we'll talk about this later in chapter 1. It's important. Okay. Hopefully this makes sense to you. Again, There's nothing really deep in what I'm doing up to now, but it can get a little tricky with some kinds of, there are exercises which will test your intuition. Hopefully the next example will not test your intuition too much. It's very basic. So I have three sets. Set A consists of elements 1, 3, 4, 5, 8, 9. B consists of elements 1, 2, 3, 5, 7. And C consists of the elements 1 and 5. And I've listed, to illustrate the notion of inclusion, I've listed all the possible inclusions in there that you have. So C is a subset of A. What does that mean? Well, you look at the elements in C, it's 1 and 5. Are they in A? Yes. So C is a subset of A. You can check that C is a subset of B. Obviously, C is a subset of C. Every set is a subset of itself by definition. B is not a subset of A. How do I check that? I have to find some element of B which is not in A, and you can see that 2 will witness this. So B is not a subset of A, and so on and so forth. Okay. And I wrote it, I mean, it's not a big deal, but C is clearly a proper subset of A, right? So I could have written it that way if I had wanted to, just to emphasize the fact that C is not equal to A. All right. So hopefully this is going well. Here's another example to illustrate how things, depending on the set that you're looking at, things can get complicated. So this is a definition that is something we're going to be looking into quite a bit in chapter 4, a couple of weeks. It's super important in computer science, prime numbers. So, and you've probably seen that in high school at some point or another. So a positive integer is said to be prime if it cannot be divided by any number except 1 and itself without leaving a fraction. Okay. You might ask, well, why is 1 not a prime? Because it's only divisible by 1 and itself. Yeah, we could make it a prime if we wanted to, but there's some nice theorems that we'd have to rewrite in some very, very nasty way if 1 were prime. We'll see that in chapter 4. You'll see exactly why we don't want 1 to be prime. So the first few primes, 2, 3, 5, 7, 11, right? So 6 is not a prime because it's 2 times 3, and so on and so forth. There are tons of questions about the prime numbers, which are difficult and interesting and fascinating. The one which is here is one of the most famous questions about prime numbers. It's called the Goldbach conjecture, and it dates back to 1742, and nobody knows how to solve this problem. So here's the Goldbach conjecture. So we have 2 sets. I stated it as an inclusion of sets to illustrate what we're doing. So the first set, A, is the set of even integers greater than 2. So 4, 6, 8, 10, 12, right? The even integers. And B is the set of all numbers which are the sum of 2 prime numbers. So these are potentially different sets. They are different sets. But Christian Goldbach, a long time ago, said, well, I think that set A is actually a subset of B. In other words, that every even number greater than 2 should be written as the sum of 2 primes. You're allowed to use the same prime, right? So 6 is 3 plus 3, 8 is 5 plus 3, 10 is 7 plus 3, or 5 plus 5. There are many ways. And it's been verified very, very, very far, but obviously you can't check all cases because there are infinitely many cases, but nobody's found a counterexample. So all even numbers are the sum of 2 primes, but that we know of, up to several millions, billions, I don't know to which point it's been verified, but we're looking for as an actual proof that it's true all the time. And if you can solve that, you'll get a nice job. I don't think there used to be prize money for this, but there was yeah, it was in Germany, and there was a big crash. The market crashed, and the prize money became ridiculously small. So I'm not sure if there's still any money involved, but certainly if you solve the Goldbach conjecture, you'll get a nice job for sure. Okay. All right. So some properties of inclusion. These are, I think, should be obvious. So if you take any sets, A, B, C, then all the following will be true. So first of all, the empty set is a subset of any set, right? And any set is a subset of itself. By definition, this is clear. The second one is clear. The first one, why is the empty set a subset of A? Well, I have to reason that every element in the empty set is an element of A. Well, that's true. There are no elements in the empty set, so there's no way to not have the empty set a subset of A. Hopefully, that makes sense to you. The second property is the one that I mentioned, is the definition of equality of sets. So if A is a subset of B and B is a subset of A, then A is equal to B. And this is a really important, I mean, it seems obvious. Hopefully it is, but it's very useful. The third one, this is really also quite clear by definition. If A is a subset of B and B is a subset of C, then A is a subset of C. Okay. And finally, and I didn't put that in because the universal set is sort of annoying sometimes. But clearly, if you have a fixed universal set, then all the sets you're considering are a subset of this universal set, right? Okay. So basic properties. Okay. Finite and infinite sets. Well, yeah. Okay, so let's say you have a set and it has n distinct elements where n is some non-negative integer. I wrote non-negative because it could be 0, right? Then we say that's our definition, that A has cardinality n. In other words, that's the number of elements in A. Okay, and in this case, we say that it is finite. So that's what a finite set is. It has, if you count the elements, it has a certain number of non-negative elements, non-negative number of elements. Yes. If this is not the case, so all the other sets, then we say that they are infinite. Okay, so non-finite in a sense. Okay. Notation for cardinality n is the one you see there. There are unfortunately many other notations for this, but that's the most common. Obviously, a set has cardinality 0 precisely when it is empty. There's only one empty set. There's only one set with 0 elements. That's the empty set. The set of positive the set of natural numbers and integers, rationals, reals, complex numbers, they're all infinite sets. Another set which is infinite is the set of primes, which is not totally obvious, right? If you've never seen the proof, we'll see it in chapter 4. It's a very, very, very nice argument. It's very old, 2,300 years ago in Euclid's Elements. It's a very nice proof that there are infinitely many prime numbers. We'll see that in a few weeks. Okay. All right, power set. Okay, so here we're going to start using our brain a little bit more, hopefully. If I take a set S, I can create a new set from it called the power set, which is the set of all subsets of S. Okay, so again, I mentioned that sets can have as elements other sets. So here's an example. So the power set, P of S, is the set of all subsets of S. So let's take a look at a simple example. If the set S consists of elements 0, 1, 2, then its power set is the following set. So what are the subsets of S? I really wish I had a blackboard, and I still, believe it or not, I've been doing this for almost a year, and I still haven't figured out how to show you slides and write at the same time on some blackboard. I haven't found a good way to do it. But what the hell? That's what it is. So the power set of S is the following. So what are the subsets of S? There's always the empty set. There it is. You can look, I've listed this in a systematic way where I looked at subsets of size 1, of size 0, the empty set, then of size 1. So there are 3 of them. Then of size 2, there are 3 of those. And then there's S itself, which is always a subset. Every set is a subset of itself. Okay. Now, this is where you're going to start having to think a little bit more. So notice that 0 is not an element of the power set. Okay, be careful. So the set consisting of a single element 0 is an element of the power set, but 0 itself is not an element of the power set. 0 is not a subset of S. Okay. In the same vein, actually what I'm writing there is basically the same thing, but the subset, the set, yep.
So can only there cannot be any single elements in as is included in a power set. Only sets can be part of a power set, right?
Yes. Yes, because I understand what you're saying. Just be careful.
Yeah,
so,
I don't have the wording yet.
No. But I none of the elements, the original elements of S, can be elements of the power set. That is correct.
Okay, thank you.
Yes, absolutely. Yeah. So in the same vein, is that another hand, or is just, oh, I should, okay, it's gone. Yes. So the set consisting of the element 0 is not a subset of the power set, but that means the same as this. If you think about the definitions, the same thing, right? So you have to parse these things. So what does that mean? If it means that 0 is not an element of the power set, that it means exactly the same thing. However, this is true, right? Because, I mean, that looks a bit nasty, but what does it mean? It means that this, which is the unique element of this set, this is actually an element of the power set. So this is true, right? Which means basically the same thing as that. These two statements mean the same thing. Okay. So it can get a little, it can mess with your mind if you try to go too fast, but if you sort of go very systematically using the basic definitions, you should be okay. Okay, so here's a little bit more on this. So what is the power set of the empty set? So the empty set has one subset itself, right? And that's it. There's nothing else. So the power set of the empty set is the set consisting of one element, the empty set. Okay. So now let's take the power set of that. Okay. And what is that? Okay. So now here's a trick. If you find that the bracketing it's just like going like what's going on, you can rename this thing. You can rename the element here. Let's call it little a, for example. This might help. Okay. But let's try to do it directly like that. So what is the power set of the power set of the empty set? Well, this is my set. What are its two? It has subsets. The empty set is a subset, right? And itself, and there's nothing else. So the power set of this power set is the set consisting, I don't know why those two S's are, but consists of two elements. One is the empty set and one is the set containing the empty set. Okay. You can try the next one. Okay. At some point, it has four elements. Okay. Now, if you notice this, if you were to try then the next one after that, you'd see that it would have 8 elements. And this is where the power set name comes from, but we'll talk about that a little later. There's a nice alternative to seeing all of this in terms of sequences and binary. So we'll talk about that a little later. Okay, but you can see it can get a little nasty. You have to be careful. Okay. Sequences and tuples. Yeah, we want to talk about products. So let's say I have a set S and I have a positive integer n. What we call an ordered n tuple of elements of S is a sequence of elements of n elements of S. And this is an ordered sequence. So this is important, that the order in which I write my elements of S is important. Okay. So for example, if I had a set that contained two distinct elements A and B, then these two n tuples, these are two tuples, which we usually call pairs, AB, BA, are different. They are different pairs because it's not the same. Think of the real plane, right? So we talk about the real line, then we take pairs of real numbers, we get the real plane, then 1, 2, and 2, 1 are different points in the plane, right? So that's the same thing. Okay. So once we have the notion of n tuples, we can talk about products. Okay, so this is a very standard construction. If we're going to talk about a little bit about databases and relational databases, if you're going to talk about those, then you need to have products to talk about relations and such. Okay, so I'm going to start by defining the product of two sets, then we'll see how we can generalize this. So I have two sets A and B. So their product, or Cartesian product, which is denoted A times B, this is the set of all pairs where the first entry of the pair comes from the set A and the second entry comes from the set B. So notice that you can't switch things around, okay? So it's important. A times B might not be the same thing as B times A. There are different sets, okay? So with my earlier notation, it's a bit shorter to write this way. A times B is the set of all pairs such that A is in A, B is in B. Sorry, I'm losing my voice. So here's a little baby example. If I have the set A consisting of two elements, 1, 2, and the set B consisting of three elements, X, Y, W, then what is A times B? So it's all pairs where the first entry will be from A, second entry is from B. So I listed all of them here, 1X, 1Y, 1W, 2X, 2Y, 2W, okay? This example shows you I didn't compute B times A, but clearly B times A is not going to be the same thing as A times B. The pairs will all be flipped, okay? Yeah, so I give an example here where the pair X1 is in B times A, but it is not in the product A times B, right? So of course, when you think about the real plane R times R, since it's the same set, then it makes no difference in which order you take it. But if the sets are different, you're going to get different pairs. Okay. All right. So that's the product of two sets. And then you can just generalize to any number of sets. Let's do it for n sets. So let's say I have a positive integer n and I have sets a1, a2 right up to an. Okay, then the product in that order of a1, a2 right up to an, which is denoted a1 times a2 right up to an, this is the set of all n tuples, ordered n tuples, where the first entry comes from the first set, the second entry comes from the second set, and so on. Okay, so a bit shorter to write, not as easy to read, obviously, but product of the A1 to AN is the set of all n tuples where AI comes from big AI for all I1 to n, okay? So I have an example here with 3. Why this? I don't know why. So I have an example here with 3 sets. Big A consists of elements 0, 1. Big B consists of elements 1 and 2. And big C consists of elements 0, 1, 2. Then A times B times C is all triples, all 3 tuples, where the first entry comes from A, second from B, third from C. So I've listed them all here. You can verify. So how many do we expect, right? I have 2 elements here, 2 elements here, 3 elements here. You may have done some basic counting in high school at some point or another, but if you think a little bit about it, we'll talk about it later anyway, but you should expect to have 2 times 2 times 3 different triples, right? So that's 12, and hopefully I got 12 different ones here, which I think is the case. Okay, all right. Hopefully this is okay. Again, there's not many counts. I mean, it's mostly definitions, right? We're building our language. Okay, some notation about Cartesian products. If I have a set A squared, as you can guess, will denote A times A, and A cubed will denote A times A times A, and A power n in general will be A times A times A n times. And I've thrown one in here, which I find is really cool. So you've seen the sigma notation, no doubt. So this is the equivalent of the sigma notation, but for products, right? So it's a big pi, P, product. So product I equals 1 to n of the AI means A1 times A2 right up to AN, okay? So if you've seen the sigma notation, hopefully this is perfectly natural. And you have seen the sigma for sure. You've done Cal 2. So I said you shouldn't know anything from Cal 2, but that doesn't count. Okay. Relations. Man, this is not the most exciting math. I mean, but we have to, what can you do? We have to define our terms. So, okay, relations. So if I want to talk about functions, I have to talk about relations, and for relational databases too. Okay, so what's a relation? Well, simple. If I have 2 sets, A and B, a subset of A times B, that's what we call a relation from A to B. Okay, so any subset, here I called it R, of A times B is what we call a relation from A to B. So it's a bunch of pairs where the first entry is from A and the second entry is from B. That's what a relation from A to B is. So here's an example. I took a set A, or my set big A would be little a, little b, little c. Big B is 0, 1, 2, 3. And I just took a bunch of pairs from A times B. So that's a relation, okay? For relational databases, most of the time, we look at relations which are where the sets A and B are equal, right? And we might have even more factors in our product. So what we call an n-ary relation on a set A is a subset of A power n. So you take n tuples where the entries all come from the same set. Okay, I'll give you some examples in just a sec. But for relational databases, these are very standard. Yeah, well, so just to illustrate this, so what's a relational database? And this is the real definition. It's a set A with a bunch of relations on A of various arity. So that's what a database is, relational database. Okay. So here's two examples. Unfortunately, I always, every time I think I should use one with more, but these are very, very standard ones. So, so genealogy. So let's take H to be the set of all humans. And you might object if you're very strict. You'll say, wait, that's not well defined because it sort of changes all the time because people are being born and dying. That's true. Well, let's just take a picture. Boom. And right now, so that's H, that's our set of all humans. So I can define a three-array relation R. So it's a subset of H times H times H. So these are triples where all the entries are humans, okay? And the relation R would be the following. It's all triples A, B, C, such A and B are the mother and father of C, all right? So of course, if we understand this this relation very well, we understand, you know, genealogy, right? You can say, oh, you're so-and-so's cousin and this and that. Or I could define H as the set of all possible humans, past and future, but not well defined either. But anyway, here's another one. Air travel. Let's C denote the set of all cities in the world. You could say cities with an airport. And here's a relation, a three-array relation on C. So it's a subset of C cubed. It's the set of all triples ABC such that there is a flight from city A to city B that stops in city B. This is actually rare, but it exists. I've actually been on a flight like that once, where your flight just, you don't change planes. You actually just stop in a city and then you go to another city. It happens. Not common, but it happens. So so that's a pretty, so but there are databases obviously for air travel that you can, I mean, they're out there. And of course, so what's the point with computer science is that you want to be able to use these databases efficiently. You have to query these databases, and that's not an obvious thing. So database theory studies how you can actually try to query databases in an efficient way, or try to show that certain queries are harder than others, and so forth. Okay. All right, so that was 2.1, our basic definitions. 2.2, we're going to define some basic operations on sets. Many of these you have seen in one way or another before. Maybe not in full generality, but they should be fairly familiar to you. Okay. Are we on time? Okay, pretty good. Okay. So let's start with this. First definition, the union. Very simple. So I have two sets, A and B. What is the union of A and B? It's a new set. The notation is A, U, B, called A union B. What is that? So how do I tell you what a set is? I have to tell you what its elements are. So what are the elements of A union B? These are the elements which are either in A or in B. Okay, so in set builder notation, it's the set of all X such that X is in A or X is in B. And I have this little potato diagram showing you an example where you have their two sets, and so the union is bigger, right? It'll contain as subsets both A and B, right? Okay, I think that's pretty straightforward. Ooh, did he use cut and paste? I think he did. Intersection. So I have two sets, A and B. What's the intersection of A and B? It's A with a upside down U, A intersect B. What is that? It's a new set. The elements of this set are the elements which are in A and in B. So the elements which are in both. So the little picture there is very useful, right? So that's the intersection of the two sets A and B. So I gave you an example here: 1, 2, 3, 6 intersect 3, 4, 6, 7, 8. The elements in common are 3 and 6. Okay, nice and easy, I think. Hopefully, yes. Okay, little extra definition. We say that this is just terminology. It's a useful name. So sets are said to be disjoint if they have no elements in common. So if their intersection is empty. And I give you a little example here in a little picture to illustrate this. Okay, so it's just a name we give to sets which have no elements in common. Okay. All right. Complement. This is a useful little operation, but it's not as clean as the other ones because it requires a universal set. So it depends on the universal set that you have. But if you are given a universal set, then the complement is a nice and simple operation. So I have a universal set U. I have some subset of U. Here I called it A. So the complement of A, and again, this is with respect to U, okay? There are many different notations for this one. The two most common are the ones that you see here: A with a bar over it, and A with a little exponent C, A complement. This is, as you can probably guess from the name, this is the set of all elements of the universal set which are not in A. So it's everything outside A, okay? So in set builder notation, it's the set of all X such that X is an element of U and X is not in A. Okay, so here's the picture tells you exactly what this is supposed to be. So here's an example. If the universal set is the natural numbers and A is the set 1, 3, 5, 7, you see here I use the three little dots. You can guess what this is. It's the set of odd numbers. Then the complement is all the natural numbers which are not odd, which are the even numbers: 0, 2, 4, 6, and so on. Okay, so that's not, I mean, that should make sense. Yes. I'm sorry, this is not super exciting, especially in video. Oh, well. Yeah. Set difference. Okay, this one does not require a universal set, which is cool. And you can probably guess from the name what this is going to be. So I have two sets, A and B, and the difference of A and B, A minus B, more commonly A set difference B. So these are all the elements. So it's the set that consists of all elements in A which are not in B. Okay, so you have A, and the picture shows you very quickly what this is supposed to be, right? So you take everything which is in A, but you remove anything that is in B. Okay, so example 1, 2, 3, 4, 5, the set consisting of 1, 2, 3, 4, 5, set difference, the set 4, 5, 6, 9. So you'll have to remove 4 and 5. So that leaves 1, 2, 3. Okay. So that's the set difference. Okay. Now I've been a bad boy and I've just basically copied down directly from Rosen's book, cut and pasted PDF. I have some basic identities about these operations. So let me show you this slide. This is the next slide. And now you're thinking, oh no, do we have to know all of these? Answer, well, actually, almost all of them are like super obvious, okay? Do you need to know them by heart and the name? No, that's not necessary, okay? What I'm going to do is just go very quickly over a few of them to show you how obvious they are. A couple of them are not obvious, and I'm going to talk about them in a bit more detail. So let's start with, but I mean, okay, here's the thing. What you should do is go through these identities and convince yourself that you understand why they're true. Okay, so that's really that will test and make you practice the notation and the notion of sets and everything we've done. That's the best practice. You just go through the table and just check that you understand every one of them. Okay, so let's start. For example, so U here is obviously some fixed universal set. So here A intersect U is equal to A. Well, yeah, because our universal set contains as a subset every set that we consider. So if you intersect A with the universal set U, you should get A back. Sorry. The union of any set with the empty set is that set itself, right? And so on. So you can go through the list like that. Sorry, man. And most of them are really straightforward. Here's another one, the complementation law. The names are, the complement of A is A. Hopefully that makes sense, right? So you have your universal set, you have your set A. You take the complement of A, that's everything that's not in A, but in the universal set. And then you take the complement of that. What is that? That's everything in the universal set that's not in A, so that's everything in A, right? If you hopefully, again, the Venn diagram, the potato diagrams are kind of cool because you can visualize what's going on pretty quickly this way. Commutative law, that's like directly from the definition, right? Associative law, I mean, yeah, I mean, hopefully this makes sense, but you have to sort of work through it. And then we get to a few ones which are not so obvious. The distributive law, I don't find obvious at all. I mean, I look at that and I don't see why this should be true. So I have to work it out. De Morgan's law, even less, or just as not obvious to me as the distributive law. And I mean, there's these things are still, to me, not obvious in the sense that I know they're true. That's different, right? To know something is true and to find it obvious, these are two different things. But I know I can work them out, okay? So in that, I'm going to do that. I'm going to work out one of these two De Morgan's laws in just a sec. Absorption law, not obvious to me either. I've always had a little trouble with that one. I don't know. I mean, I have to work it out, right? I have to read it, to parse it, think, okay, this makes sense. I mean, the first one is not so bad, right? Because what it says is that if you take the union of A with, wonderful, with A intersect B, you should get A back. So let's think about this. A intersect B, this is a subset of A, right? It's all the elements which are both in A and B, so it's contained in A. Now, if you take the union of A with one of its subsets, you're not going to get anything more than A, so you get A back, right? And it's sort of the same thing here. So A union B is a set that contains A as a subset, and then you intersect with a smaller set, so you're going to get A back, okay? Again, Venn diagrams are very useful to visualize what's going on, okay? And the last one is easy also. So let me talk about De Morgan's law, because they are actually also, these are really important. So let's take a look at De Morgan's laws in more detail. Okay, so what does De Morgan's law say? There are two of them. Is that the complement of the intersection is the union of the complements, and vice versa. The complement of the union is the intersection of the complements. So you notice how the complementation flips the operation from intersection to union and union to intersection. which is something you've probably never seen before with basic arithmetic with the real numbers. There is no such duality with a complement. The minus, the negation does something like this, but it's anyway. So what I'm going to do is I'm going to prove the first one. I'll leave the second one as an exercise. And I mean, it's for sure it's listed in the exercises I've put on Leia. So how am I going to show that these two sets are the same? Okay, so this is really important because this is going to come back a lot at many different levels. So I want to show that two sets are equal. Sometimes it's possible to show two sets are equal directly. But the most common way of showing two sets are equal is exactly as I've written here, is to show that there's one inclusion this way and the other inclusion the other way. Okay, so remember, two sets are equal if they have the same elements. So here, little I says the elements of the left-hand set are all elements of the right-hand set. And the second one says the elements of the right-hand set are all elements of the left-hand set. So basically, they have the same elements, and hence they must be the same. Okay, so let's try to argue this. This would be better on iPad, but okay. Let's just go through this. Maybe next time I'll redo it if necessary on writing it out. Okay, so let's see. So I want to show, so here's, okay, so that's the first overall technique to show two sets are the same. Inclusion this way, inclusion that way. Nice and simple. Now I want to show an inclusion. So what does it mean for this set to be a subset of this set? By definition, it means every element of this is an element of this, right? So what do I do to show this? I pick an element here, arbitrary, and I show that it must be here. Okay, so that's what I'm going to do. So I choose an X, whatever. I mean, choose not an arbitrary X. I take some X in the complement of the intersection, and I want to show that it's in the union of the complements. Okay, so now what do? I analyze what it means for X to be in the complement of A intersect B. It means it is not in A intersect B, right? So we don't need to mention the universal set here. Everything's in the universal set. We just forget about it. Okay, so X is in the complement of the intersection means it is not in the intersection. Okay, what does that mean? All I'm doing is applying definitions here. Okay, so there is absolutely, there is zero creativity here. I'm just following the rules one after another. Okay, so X is not in the intersection means either it's not in A or it's not in B. That's what that means, right? Because if it's in both, it's in the intersection. Okay. What does it mean not to be in A? It means you're in the complement of A. That means exactly the same thing. Not to be in B means you're in the complement of B. So then X is either in the complement of A or in the complement of B. And so by definition, that means X is in the union of the complements. Okay. All of that for that. Okay. But I implore you to try to go through this argument. I mean, it's not like this is the most exciting result in the history of math. It's not, okay? But the process is going to help you out tremendously. If you can actually go through what I've just done here by yourself, saying, okay, this, and get to the end, you'll be training your brain to work in a proper way, analyzing the definitions and just applying them. Okay, and this is fundamental. We wanted to automate this a little bit. Okay. The second one is similar. I don't want to go through the slide. You can read it by yourselves, and next time I'll do it writing it out on an iPad. It's much better. Okay. Are there any questions, comments about this or anything else to this point? I'm almost done for today. Okay, good, excellent. Oh, whoa. Yes, that woke you up. Okay, do I want to do that? I don't want to do that. I don't want to do that either. Okay, so I'm going to skip right to the end for a little aside here. Um, I'm gonna finish with this. Um, so um, I said that you have to be careful when you talk about, you know, the set of all sets and things like that. And so Cantor, um, I mean, there was a huge debate in the 19th century when Cantor came up with his set theory because it was like super powerful. But many mathematicians were really against it. They thought it was just the most awful thing they had ever seen. And they were right in one little areas that it wasn't really precisely defined and you could get into trouble, and that's what happened. But eventually everything was cleared up later, but you had to work at it. um, Bertrand Russell, if you don't know the man, a great philosopher and mathematician, um, Nobel Prize. In 1901, there's a whole story behind this, which is actually funny, except for the poor guy who wrote. I mean, a mathematician. I should have looked up his name. I can't remember his name. He wrote this big book on logic, and just when he was about to publish it, Russell wrote to him with this, said, "Oh, by the way, look, there's this little problem here," and so the guy just took the book and threw it in the garbage. Um, but anyway, other story. So here's the paradox. Here's what you have to be careful with. So suppose that, like we did, we can just say a set is anything with elements in it, and that's it, right? Um, so so let's consider the following notion of a set being normal. So I'll say a set is normal if it's not an element of itself. Okay. So for example, natural numbers, integers, real numbers, these are normal sets because they are not elements of themselves. Okay. The empty set is also normal. Okay. But there are sets in naive set theory, if you allow anything to be defined as a set, there are sets which are not normal. So for example, the set of all sets, right? So this is a legit thing, right? So it's the set whose elements are all possible sets. Well, itself is an element of it, of this set, because it's a set, or the set of all mathematical concepts. This is an not normal using our definition because it's an element of itself. Okay. So here's what Russell did. He said, okay, so some sets are normal and others aren't. So let's build a new set. We can build whatever set we want. It's the set of all sets that are not normal. Okay. So that's a legit set. And the question is S normal or not? That's a good question, right? So suppose S is normal. What does that mean? It means it's not an element of itself. But S is the set of all sets that are normal. So if S is not an element of S, it can't be normal. So we have a problem. Okay. So if S is normal, it can't be normal. So that's a contradiction, right? Conclusion, S is not normal. But if S is not normal, it means that S is an element of itself by definition of the set S. Okay. Sorry, by definition of normal set, right? But if S is an element of S, if you look at the definition of S, it contains only sets which are not normal, are normal. Sorry, I'm even making it more confusing than it already is. Sorry. So S is normal. Okay, let's try that again. Okay, if S is not normal, by definition of normal set, S is an element of S. Now you look up what S is. It is the sets which are normal. But I made the assumption that S was not normal. So if S is not normal, it's normal. And if S is normal, it's not normal. In other words, this set S is crap. Okay, there's no such, it makes no sense whatsoever. Okay, so we've run into a big problem. Okay, so basically what this says is you can't just define sets of things just like that without being careful what you're doing. Okay, what's unfortunate is, I mean, if you're just playing with finite things, you'll be fine. You're not going to run into this problem. But still, it turns out that, so this looks like it's like, you're smoking something and who cares, right? It's not relevant to anything, but it is like super relevant actually to computer science, because 35 years after Russell, Alan Turing would use basically the same arguments to show some wonderful things that I'll try to talk about a little later. But Turing showed that some important problems could not be solved by a computer. And he used exactly the same argument. He basically used Russell's argument. And so this is actually pretty cool. I'll try to tell you about that a little later. Okay, so that's why we have to be careful. But in the where we're playing, this is not going to happen. So that's fine. Okay. All right. So that'll be it for today's episode. Now, since you probably just got the book and you just got this, it's sort of pointless to have you work online on anything. So we'll just call it a day. And let me just stop this. So I'm stopping the recording.